When a single user requests a password reset, the operation is trivial. An API accepts the request, validates it, and fires a payload to an external provider, like Twilio or Apple's push notification service. A few milliseconds later, the payload arrives. Scale that to 1 million simultaneous requests, and that trivial operation becomes a system-killing bottleneck. If the API waits for an external provider to respond to every request, network latency compounds. Worker threads block, memory exhaustion triggers crashes, and external providers issue rate limits that bring the entire pipeline to a halt. Scaling to this level requires a redesign of the data path to support 3 specific non-negotiable guarantees. First is delivery. A notification that never arrives is a catastrophic failure. If a system silently drops a fraud warning or a security code, the user's account is compromised without their knowledge. Delivery is the baseline. Second is timeliness. An authentication code delivered 2 minutes after it expires has 0 value. The system must route time-sensitive alerts fast enough to remain actionable. Third is relevance. Hitting a user with a promotional blast during their configured quiet hours or after they have opted out violates both the user experience and data privacy laws. Meeting these guarantees during a massive traffic spike requires a decoupled asynchronous architecture. In a synchronous pipeline, the API receives the request, writes to the database, and waits for the provider's acknowledgement. If the provider degrades and network response times spike to 5 seconds, the internal API is forced to wait those same 5 seconds. This couples ingestion to unpredictable latency. An outage prevents enqueuing new jobs. To fix this, we decouple the services. The API writes to the database, drops a job into a queue, and immediately returns an accepted response. The message queue acts as a shock absorber. When traffic spikes, the ingestion layer captures the requests instantly. The queue fills up, and dispatch workers drain it at the exact rate the external provider allows. However, a single shared queue creates a new bottleneck. Funneling push, emails, and SMS into one path leads to cross-channel starvation. If an email provider hits a quota, retries clog the queue, trapping critical push alerts. To fix this, the single queue splits into 3 parallel tracks: push, email, SMS, each feeding its own isolated pool of worker nodes. An email backlog should have no impact on SMS throughput. This isolation contains failures to their specific channels. It allows for independent scaling of workers, providing the control needed to manage massive volume. Decoupling introduces a consistency risk. If a dispatch worker successfully calls Twilio but crashes before updating the database, the job isn't marked complete, leaving the message in an ambiguous state. When another worker picks up that job, it will send the same notification again. True exactly once delivery across external networks is a myth. Distributed transactions are too slow for high-throughput systems. Engineers instead architect for at least once delivery, managing the risk of duplicates through specific state tracking mechanisms. The outbox pattern handles internal state. Before the worker even attempts to contact the provider, it updates the notification's database status from queued to dispatching. This atomic state transition acts as a lock, ensuring no other worker can claim the job while the network call is in flight. For external safety, you rely on provider-side idempotency keys. A deterministic hash of the campaign ID, user ID, and channel ensures the provider discards duplicate requests for the same job. With a stable key, a background sweeper can safely handle worker crashes. It identifies jobs stuck in the dispatching state and requeues them using the same idempotency key, allowing the provider to safely ignore the duplicate. System reliability depends on deterministic state machines that make hardware crashes invisible to the end user. Transactional messages are predictable, but a marketing campaign targeting 20 million users presents an entirely different stress test. Expanding a single campaign into 20 million notifications triggers extreme write amplification. Attempting to render personalized text for every user at creation time generates gigabytes of data that can instantly lock a database. Deferring the rendering solves this. You store only the template ID and targeting parameters, allowing the dispatch worker to compile text at the last millisecond. The expansion happens asynchronously. A background fan-out worker pages through the target database cohort, pulling users in batches and pushing individual jobs into the channel queues. If a worker crashes halfway through, an unprotected system duplicates millions of notifications. To ensure a safe restart, the worker executes a checkpoint. writing the last processed user ID back to the database. A unique database constraint on the campaign and user ID provides the final backstop. Even if a race condition occurs, the database will physically reject duplicate entries in the queue. At this volume, a standard relational database will suffer severe index contention. The concentrated insert spike will lock the entire system. Sustaining this throughput requires write-optimized stores like Cassandra or DynamoDB. These systems use log-structured merge trees to turn random inserts into efficient sequential disk writes. Handling this volume requires managing the physical constraints of database writes through asynchronous expansion and checkpointing. When marketing blasts collide with security alerts, the system needs strict traffic control. If 50 million promotional jobs flood the pipeline, a critical fraud alert must still reach the user immediately. In a single queue system, that critical alert gets trapped behind millions of marketing jobs, ensuring it arrives too late. The solution is a two-tier priority system. By using separate physical queues, the system creates a fast lane where critical alerts bypass all promotional traffic. Dedicating 80% of workers to the critical queue ensures one-time passwords bypass rate caps and quiet hours. These messages are mathematically guaranteed to process without delay. But separate queues do not protect you from external limits. If an email provider issues a 429 too many requests response, the dispatch workers must pause. If hundreds of isolated workers independently back off and retry at the same millisecond, they trigger a thundering herd, DDoSing the provider. Coordinated backoff prevents this. The first throttled worker writes a pause timestamp to a shared Redis cache, aligning the entire fleet's schedule. Prioritizing traffic and coordinating pauses provides a structural defense that stops a high-throughput system from destroying its external partners. We review the complete macro architecture, the API layer, write-optimized database, fan-out service, two-tier queues, and rate-limited workers. To handle 1 million notifications per second, the system must route 700,000 pushes, 200,000 emails, and 100,000 SNS messages every second. Decoupling the API from the dispatch layer allows the ingestion nodes to capture this million request spike without blocking. The outbox pattern and deterministic idempotency keys protect these messages from the inevitable reality of worker node crashes. Two-tier physical isolation ensures that one-time passwords execute in under 5 seconds, regardless of promotional volume. Senior-level architecture assumes constant failure and isolates it. A 1 million notification per second pipeline functions as an asynchronous state machine, engineered to absorb chaos and guarantee delivery.